Okay, we're going to look at a couple examples of the fundamental theorem of calculus. The first one is if we rewrite 6x squared as the derivative of 2x to the third. That's the first example. Let's first make sure that that's correct. If we do the derivative of 2x to the third, the 3 is going to come down, and your new power is going to become 2. So that'll be 3 times 2 times x squared. So yes, we do get 6x squared. So 6x squared is the same as the derivative of 2x to the third. And the fundamental theorem of calculus says that the integral and the derivative kind of cancel each other out. So your answer is going to be whatever's left inside here, and so that's going to be 2x to the third. Of course, you could just use the power rule to do this. The x squared would become x to the third, and then you'd have to divide by 3. Don't forget the 6 in front of it. This would also give you 2x to the third. So you can use a power rule, or you can use the fundamental theorem of calculus that basically says the integral of a derivative cancels. So this kind of cancels out, and you'd be left with 2x to the third. Now let's take a look at the other type of fundamental theorem of calculus. We're calling this fundamental theorem of calculus number 2. And that's if you go the other direction. So that's if we do the derivative of the integral. We're also saying that those two things cancel, and your final answer is just whatever's inside. Now we can check to see if this works because we know how to do the integral of 30x to the fourth. It would be x to the fifth over 5, and then don't forget the 30 in front of it. So that piece ends up equaling 6x to the fifth, and we can do the derivative of 6x to the fifth. The 5 would come down, that would give you 30, and then the new power would be 1 less, so the new power would be 4. So you see it does work, but the main concept here is for the fundamental theorem of calculus, the integral of the derivative or the derivative of the integral are basically going to cancel. That's the main idea behind it. Now let's go ahead and do some actual examples. Now instead of doing an indefinite integral, we're going to do a definite integral, so we're going to actually have bounds this time. If we didn't have bounds, then basically these two things would cancel, and we would just get 3y squared. But because we have bounds, we're going to have to plug in the number. So that would give us 3x squared. And then we got to do the chain rule, so we got to do the derivative of that number. So we're going to do the derivative of x. Okay, then we're going to do minus. Then we're going to plug in the 2. Plug the 2 in. And then we need to do the derivative of 2. And the derivative of 2 is 0. So this piece over here is going to cancel. And we'll just be left with this piece, 3x squared. Let's do another one. We're going to plug in the 5x. That'll give us 3 times 5x squared. And we need to do the derivative of 5x. The derivative of 5x is just going to be a 5. Now this part right here is going to give me 25x squared. And then times 3 is 75x squared. So I evaluated at 5x. Then I'm going to do minus. And now I'm going to evaluate it at 2. So we got to plug in the 2. That'll give us this piece here. And then we need to do the derivative of 2. The derivative of a constant is 0, so this piece is just going to cancel. Final answer is 375x squared. Let's try another example. Okay, now they're giving us a function that's equal to an integral. And they want us to find f prime of 2, so we're going to have to start by finding f prime of x. So we need to do the derivative of this integral, and that's how we'll get the derivative of f. So here we go, we're doing the derivative of an integral. Whenever you do a derivative of an integral, you can plug in the top bound. So plug in the x squared, and then we do the derivative of x squared. Then we do minus, and then we'll plug in the lower bound, so plug in our x, and then we got to do the derivative of x. So this piece will be x to the fourth. The derivative of x squared is just 2x. This is just 3x squared. The derivative of x is 1. So we can simplify this just a little bit. 3 times 2 gives us a 6. And x to the 4 times x gives us x to the 5. All right, so this 1 times 1, it just gives you 3x squared. And that's pretty much it. We now know what f prime of x is, but they wanted f prime of 2, so we need to plug in the 2 right here. And then we'll know f prime of 2. So we plug the 2 for the x, and after simplifying this stuff, we get 180. So just as a reminder, this is 2 to the 5 is going to be 32. So we get 6 times 32. 2 squared is 4, so it's going to be minus 12. And as you can see, 32 times 6 is going to give us 192. So this becomes 192 minus 12, and that's how I'm getting 180. Okay, now we're going to do a free response type of question. This one says, find where the absolute maximum value occurs for the function f of x on the interval from 0 to 17. Now, this is a capital F, so it's going to match up with this capital F. So the graph over here is the lowercase f, so that's something different. That's not the capital F. Now, our capital F is equal to this integral. I want you to notice that we can do the derivative of both sides. The derivative of capital F is going to be capital F prime. And then when I do the derivative of this integral, I'm going to plug the x in. That'll give me f of x. Then I need to do the derivative of x, which is a 1. Then I do minus, and I plug the 0 in. That's going to give me f of 0 times the derivative of 0. So I'm going to end up getting times 0. This piece becomes 0, and this piece becomes f of x. So f prime of x is equal to the little f of x. So what I could do is I could just rename this graph if I want to. I'm going to bring this over here. I'm going to call this graph f prime of x, the big F. And that's because after doing the derivative of capital F, my final answer was little f. Now again, we want to find the absolute max of big F. And we have the derivative for big F. This graph is the derivative for big F. So anywhere this graph is above the x-axis, that means our capital F is going to be increasing. So our capital F is going to be increasing in that blue region. And anywhere our derivative is negative, so anywhere our graph is below the x-axis, that's where our capital F is going to be decreasing. Again, we are looking for the maximum for capital F. So our capital F is going to be increasing all the way until you get to the point x equals 11. At this point right here, capital F is going to start decreasing. And capital F is going to decrease all the way until you get to x equals 17. So capital F is increasing, and then capital F is decreasing, and that spot where it changes is going to be at x equals 11. So that's where capital F has its maximum. It's going to be at x equals 11. And that spot would be an absolute maximum as well as a relative maximum. So it would count for both. We were looking for the absolute maximum. Okay, let's go look at the next example here. This is the same example, it's just a different question. First, they wanted to know where the maximum occurred. And so that's going to be an x value. Now it's asking what is the absolute maximum. So now we need to find the y value. So if the absolute maximum occurs at x equals 11, then we need to plug an x equals 11 into our f function. If I plug an 11 there, I'm going to get an integral from 0 to 11. So there'll be an 11 right here. Okay, there we go. I put the 11 there. And now we have that f of 11 is equal to the integral from 0 to 11 of this function right here. Now, we can think of the integral from 0 to 11 as the area under the curve from x equals 0 to x equals 11. When you're above the x-axis, you get positive. When you're below the x-axis, you get negative. And that's why I wrote negative 12 here. But let's figure out, where am I getting these numbers from? How do I figure out that that's 15 and this is 22 and this is negative 12? So let's take a look. It's a little bit of geometry. For the first one, I'm going to go ahead and do the area of a trapezoid. The area of the trapezoid is going to be the width. So this is my width right here. And then times the average height. So one of my heights is 2. The other height is 4. And for average height, you got to add them up and divide by 2. So that's how I'm getting a 15. I end up with 30 over 2, which is 15. And that's the area of that first region right there. For the second region, I'm getting 22. Let's take a look at how I'm doing that. That's also a trapezoid. This time, the width is going to be that red line on the left side there. And my first height is going to be this distance right here. So that's 5. That's where I'm getting the 5 from. And my second height is going to be the distance along the bottom. So that height is 6. So the width is 4. And the two heights are 5 and 6, but you need average height. And that's why I'm dividing by 2. Okay, if you multiply the top, you get 44, and then divide by 2. That's where I'm getting the 22 from. Okay, for this bottom triangle down here, we're getting an area of negative 12. The reason why it's negative is because you're below the x-axis. So for an integral, that would be negative. But I'm calculating the area by doing the area of a triangle. The area of a triangle is going to be 1/2, and then the base times the height. The base is going to be 6, so here's my base. And the height is going to be 4, so here's my height right here. So you end up with 1/2 times 24, and so I'm getting 12. Again, I'm calling it negative 12. And the reason for that is because you're below the x-axis. So for an integral, you would get a negative value when you're below the x-axis. Remember, an integral is kind of like a Riemann sum, except that it's an infinite number of rectangles. And each rectangle is going to have a negative y value when you're below the x-axis. And that's because the height of each of these rectangles is going to be a negative value. It's a negative y value. Okay, now we can go back and we can do f of 11, because now we can do the integral from 0 to 11. It's basically the area from 0 to 11. So we'd have to add up all this area here. And we added them up separately. So the first one gave us 15. The second one gave us 22. So altogether we get 37. So that integral is going to give us 37. Remember, that integral was f of 11. So when x is 11, our function has a value of 37, and that's the absolute maximum value. 37 is the absolute maximum value. All right, this one is basically the same example, except that we have a function called g now. And instead of going from 0 to x, we're going from 5 to x. So it's slightly different. Of course, when we do the derivative, we're still going to get f of x. So this graph over here is the derivative of g. So I can just rename it if I want to. I'm going to call this graph g prime of x. Now, if I have a graph of g prime of x, how can I find g double prime? Because that's what this question's asking. It wants us to find where g of x is concave up, going from 0 to 17. So I'm trying to find out about g. I want to know where g is concave up. So I need to know the second derivative of g. I do have a graph of the first derivative. So to get the second derivative, I would need to do one more derivative. If I do the derivative of g prime, that would give me g double prime. Another way of saying the derivative of g prime of x is I could do slope of g prime of x, because the derivative is the same thing as a slope. So let's replace derivative with slope. So the slope of g prime of x is the same thing as the derivative of g prime of x, and both of those would give me g double prime of x. Now, if you look closely, you'll see I've already calculated the slope of g prime of x, and I've written those numbers here. Now, let me show you how I get this. I'm saying that the slope of this line is 2/5, and that's because I go up 2, and then I go right 5. You can see I'm going right 5. So the slope there is 2/5. The important thing is that the slope is positive. When the slope is positive, that means our second derivative is positive. And when their second derivative is positive, it means your original function is concave up. I want you to notice that the slope from x equals 5 to x equals 10 is just going to be 0. It's a horizontal line. And then I'm saying that the slope of this line is negative 4 because we go down 4 and we go right 1. You can see we do it again. We go down 4, we go right 1. So the slope of that red line is negative 4. That means the second derivative of g is going to be negative from x equals 10 to x equals 12. So g would be concave down on that interval. And then this last line over here, you can count the slope. We go up 4, and then we go right 5. So the slope is going to be 4/5, but it's positive. So that means g double prime is going to equal positive 4/5 on that interval from x equals 12 to x equals 17. Again, when your second derivative is positive, your original function is going to be concave up. So we have two regions where our function g is going to be concave up. It's going to be from x equals 0 to x equals 5. And it's also going to be from x equals 12 to x equals 17. So here's our final answer. This is where g is concave up, because that's where g double prime is positive. I do want to point out that your intervals for concave up and for concave down are always going to be open intervals. So don't use brackets for that. Now this is a little bit of a summary. We're talking about where g is concave up. This says that g is concave up when g double prime is positive. Again, that's what we already said. When g double prime is positive, that's where g is concave up. Here's another example. G is going to be concave up when g prime has a positive slope. So here's the slope of g prime. You can see where it's positive, I put a plus, and that's where g is going to be concave up. Here's another way of thinking about it. G is concave up wherever g prime is increasing. So that means g prime, this is the graph of g prime, the graph has to be increasing. So this graph has to be going up, basically. And that's where g would be concave up. So there's a lot of different ways that you can think about it. Make sure you understand the difference between positive and increasing. Let me point out an example of that right now. This graph, don't worry about what it is. This graph is positive when the graph is above the x-axis. So all of this green part is where this graph is positive. This graph is negative when the graph is below the x-axis. So that would be the red part of this. That's where this graph is negative. So that's what positive and negative means. That's not the same as increasing. This graph is increasing on this blue part right here and this blue part over here. That's where this graph is increasing. This graph is decreasing in this green area right here. And of course, this graph is constant from x equals 5 to x equals 10. So don't mix those up. Make sure that if you say positive that you mean positive, and when you say increasing, make sure you mean increasing. That's a common mistake on the AP test. Students always get questions wrong because they mix those two things up. Okay, we already did the work for this one. We just did an example where we found out where our function was concave up and concave down. And now we want to know, where does our function g have inflection points? So that would be a spot where g double prime changes signs. That's where our second derivative changes signs. So we can see easily that our second derivative is positive, then 0, then negative, and then positive. So where does our second derivative change, either from positive to negative or from negative to positive? Well, it would be only at this spot right here, only when x is equal to 12. So that means that g will have an inflection point when the second derivative changes signs, or another way of thinking about it is where your first derivative changes from either increasing to decreasing or from decreasing to increasing. The example that we had was our g prime changed from decreasing to increasing, and that happened at x equals 12. So the inflection point is at x equals 12. There is no inflection point at x equals 5 or at x equals 10 because our second derivative does not change signs there. At those spots, the second derivative goes from positive to 0 and then 0 to negative, but it has to change either from positive to negative or negative to positive. That's the only way that g will have an inflection point at that spot. Okay, this is our last example. It says find the formula for g on the interval from x equals 10 to x equals 12. So that's going to be, if you look at the graph, that's going to be this part right here. So we're going to ignore the rest of the graph, and on that interval, our g prime is just a line. So our g prime can be written as y equals and then mx plus b, because it's just a line. Now you can actually count the slope. The slope goes down 4 and right 1. So the slope is going to be -4. So we can just plug that in right now if we want to. And then we'll just need to find the b. In order to find the b, we're going to have to plug in a point somewhere on the interval from 10 to 12. So I'm going to plug in the point 11, 0. And if I plug in 11, 0, I'm going to be able to solve for the b. The 11 is the x, so I plug in for the x. I plug in an 11. And the 0 is the y, so I'm going to go ahead and plug in a 0 for the y value. In this case, it's our g prime value, but that's kind of like the y value. Okay, you see I'm getting -44, so I'd have to add 44 to both sides, and then I figure out that b is equal to 44, so I can plug in a 44 for the b. And now I have the equation for g prime of x on the interval from 10 to 12. Now, one of the most important things you have to understand is I can only plug in a point that's on the interval from 10 to 12. So any of these 3 points would be good. You cannot plug in the point 84 or something like that. That would not work. Okay, now that we've found g prime of x, we want to find g of x, so we're going to need to do the integral. I'm going to go to the next page. Okay, we just found g prime, and it's equal to this line only on the interval from 10 to 12. So that represents this over here. I highlighted it on the graph. Now that's g prime, but we want to find g. So we're going to need to do the integral. If we do the integral, we'll have g, but the problem is we'll end up with this plus c piece. So we're going to have to solve for the plus c by plugging in a point. Now on the last example, we plugged in 11, 0, but 11, 0 was a point on g prime, so we're not going to be able to plug it into g. In order to plug a point into g, the point has to land on the function g. So this point that lands on g prime is no good. We also need our point to have an x value between 10 and 12. Let's go ahead and plug an 11 into our g function. That would give us the integral from 5 to 11. We already know that because we already calculated it. It's basically the area over here on our graph from 5 to 11, and we know that that's 22. So that gives us a point for g. On the g function, when you plug in an 11, you get 22. So 11, 22 is a point on g. So we can use that point to solve for our plus c. Now this video is already getting too long, but the 11 would go here, and the 22 would go over here. And when you solve for your c, you would get -220. So I'm going to skip that step only, just based on time. I'm running out of time here. This video is already way too long. But that would be your final answer. The function g would equal this on the interval from x equals 10 to x equals 12. Okay, there we go. We put it in a green box, and that's our final answer.